Good morning. Today we're going over our second homework assignment for chemical equations. And this one is going to focus a little bit more on just oxidation reduction and precipitation reactions. So we've got 16 problems here, and to start us off, we're looking at oxidation, reduction, oxidizing agents, and reducing agents. So just as a reminder, oxidation is what happens when something loses electrons. And since electrons are negative, that means you're becoming more positive. It's an R, okay? And reduction happens when you gain electrons. And of course, since electrons have a negative charge, that means you would be becoming more negative. And then of course, because we want to make things difficult, that's not true, but it might seem that way. Anything which is being reduced is known as the oxidizing agent, and the thing which is oxidized is known as the reducing agent. Because these things have to happen together. You can't have oxidation without reduction, and vice versa. Because if I'm losing electrons, they have to go to somewhere. And if I'm gaining electrons, they have to come from somewhere. So if I'm being reduced, then I'm helping something else be oxidized. I myself am gaining electrons, but I have to give them to somebody, get them from somewhere. Therefore, I'm helping something else be oxidized. So what we're going to look at here is the first reaction, calcium plus oxygen makes 2 CaO. And we could balance it. The balancing actually doesn't change our analysis of what's going on here. But essentially, the first thing we're going to do is assign electrons, or basically assign charge, because that's going to be relative to electrons. I could do this in a different color. So calcium here looks like elemental calcium. It's a solid. So it has an oxidation number of 0, or a charge of 0. And oxygen, same story. Elemental state, charge of 0, oxidation number of 0. Now I am an ionic compound. And ionic compounds, we're just looking at the ion charge. Calcium's in group 2, so it has a charge of +2. Oxygen is in group 6, so it has a charge of -2. I verify that those must be correct because the charges must cancel to make a neutral compound. And then I can see, all right, calcium became more positive. That means he lost electrons, so he was oxidized. And oxygen became more negative. That means he gained electrons, so he was reduced. So what gets oxidized? Calcium does. What gets reduced? Oxygen does. We can play the same game here with the next one. F2 plus lithium goes to form LiF. And we could balance this. Doesn't affect our analysis, but that's okay. Elemental, neutral, elemental, neutral. Ionic compound. Lithium's in group 1. Fluoride's in group 7. And those must be the right charges because they've got to cancel. So fluoride became more negative, so that means that it was reduced, gained electrons. Lithium became more positive, that means it was oxidized. If this seems counterintuitive, that reduction should be gaining, that is, because reduction usually think is something going down. But instead think, if you are reduced, then your charge goes down because you become more negative. That's what goes down. That's what gets reduced is the charge, because you're gaining negative charges. All right, so we said fluoride reduced, lithium oxidized. Okay. Now identify the oxidizing agent and the reducing agent. It's exactly the opposite of what you think. The oxidizing agent is the thing which was reduced, and the reducing agent is the thing which was oxidized. So here we see aluminum went from 0. Here it's in a compound, so it's +3, so it became more positive. It was oxidized, so it was the reducing agent. Therefore, this looks like it must have been reduced and therefore be the oxidizing agent. Is that true? It went from 0 and now it's -1 because it's in an ionic compound. So yes, that's the oxidizing agent. One way to think of the agent is that, for instance, a real estate agent doesn't himself or herself buy a lot of real estate. He helps somebody else do that. So the reducing agent is not itself reduced. He helps somebody else do that. So if that's one way to help you remember, reducing agent does not mean I'm being reduced, that it's the opposite, that might work for you. Okay, same story, elemental, elemental. So these both have a charge of 0 to start. Ionic compound, magnesium's +2, oxygen's -2. So I went from 0 to -2. I became more negative. I must have been reduced. That makes me the oxidizing agent and the reducing agent. Oxygen, it's called an oxidizing agent because oxygen does this a lot. Not because oxygen is oxidized, but because it's an oxidizing agent. Oxygen in the air will react with lots of metals to make those metal oxides. Okay, in mitochondria of the human cells, we've got these reactions for the electron transport chain. Iron is going from iron 3+ to iron 2+, and you see that in the process, he has to pick up an electron, right? That's what makes his charge go down. So that would be reduction, right? I am gaining electrons, my charge goes down. Here, you could see I'm losing electrons, therefore I become more positive. That's oxidation. So we could actually write this out in the reaction where we show the electron. Now, of course, that has to go somewhere. This would have to come from somewhere. So this is kind of only half of what's happening, right? If reduction is happening somewhere, something else has to be oxidized. And if something is to be oxidized here, something else needs to be reduced. And that's just an electron transport chain like the NAD and the NADH, or the FAD, the FADH2. Those are the compounds which are then being oxidized or reduced for the other half of that reaction. Okay, oxidation number on sulfur and calcium sulfate is what? Right? CaSO4. These examples were pretty straightforward because we were making ionic compounds, and the rules for oxidation numbers have to do with, if I'm neutral, it's the same as the charge. So if I'm neutral, then it's 0. If I'm an ionic compound, I can look at the charge of the ion in the ionic compound. This gets a little bit more tricky because I have covalent bonds. So the first thing we do is recognize this is an ionic compound where calcium has a charge of +2 and the sulfate, the whole thing, has a charge of -2. So the oxidation number on calcium is +2. That's easy. Okay, but we wanted to know the sulfur and not just the whole sulfate, but just the sulfur in the sulfate. So the whole sulfate has a charge of -2. And now, in order to say what's the oxidation number on each atom, we have to follow the rules that I gave you in the lecture notes for anything with covalent bonds. The rule said if I've got covalent bonds, I'm going to assign hydrogen first if I have it, which I don't. And then if I don't have hydrogen, then I will assign fluorine if I have it, which I don't. And if I don't have fluorine, then I assign oxygen if I have it, which I do. And what do I assign oxygen? I assign it just like it's an ion in an ionic compound, even though it's not. I'm going to say it's -2. Since there are 4 oxygen atoms, each at -2, that gives me a total contribution of -8 for the quote-unquote charge or oxidation state of the sulfate. Since I have 2- that are not accounted for, that tells me that the sulfur has to be as if it were a charge or an oxidation number of +6. +6 minus 8 gives me the overall charge of minus 2 because the sum of the oxidation numbers has to equal the charge. It's like I'm treating this like it's an ionic compound where we're looking at priority based on electronegativity. So since oxygen is more electronegative, it gets to have the negative charge, and then you could just deduce then what sulfur is left with. So sulfur is plus 6. Right? Okay, in these reactions, identify what is oxidized and what is reduced. All right, I've cleaned my slate here. So if we've got zinc, zinc plus chlorine goes to form zinc chloride. I think I was... Here, oxidation number of 0 because it's neutral, no charge. Same story here. Here, ionic compound. I don't know zinc because it's a transition metal, but I do know chlorine because he's in group 7. And since there are 2 of them, H at minus 1, that means my zinc must be plus 2. Right? So, zinc became more positive, so it was oxidized. Chlorine became more negative because it was reduced. Zinc oxidized, chlorine reduced. There we go. Next, I've got chlorine plus sodium bromide goes to form sodium chloride plus bromine. And here elemental, so that's 0. This is an ionic compound because I have a metal with a non-metal. So group 1 is going to be plus 1, group 7 is minus 1. Same story, metal, non-metal, group 1, group 7, so plus 1, minus 1. And bromine is 0. Pardon, that's Br2. Okay, so here we see if you could assign oxidation numbers, that it tells you what was oxidized and reduced. You just follow the math. Cl went from 0 to negative 1, so it became more negative, it was reduced. Sodium went from positive 1 to positive 1, so it wasn't oxidized or reduced. And bromine went from negative 1 to 0, it became more positive, it must have been oxidized. So the chlorine was reduced, bromine was oxidized. The numbers tell you what the answer is. Okay. Next we've got lead oxide, lead 2 oxide I should say, decomposes to form lead and oxygen. Add ionic compound, lead is a transition, so we don't know, but oxygen's minus 2, therefore this lead needs to be plus 2. This lead is 0, and that oxygen is 0 because these are elemental. So hopefully you can see lead became more negative, so it was reduced. Oxygen became more positive, so it was oxidized. Just like that. Okay. Now this one looks really tricky, but it's actually super easy. It's the easiest one we've got here because the oxidation number is the same as the charge. So if they give us charges like ion charges, at first it's like, oh, that's really busy, and then it's like, oh, well, they actually just told me what the oxidation number was because it's the same as the charge. That's really sweet. Literally the same. So this then has an oxidation number of plus 3. This one has an oxidation number of plus 2. This one has an oxidation number of plus 2. This one has an oxidation number of plus 4. And then you can see the Fe went from plus 3 to plus 2. So the charge went down, it was reduced. And the Sn went from plus 2 to plus 4. The charge went up, it was oxidized. So this was nice because we don't have to deduce the charges like we kind of had to do with some of these other ones. It just gave you the charge. Okay, in this reaction, what is the oxidizing agent and why? So if we write this one out, nickel, oh, here we go again. Okay, nickel plus copper 2 chloride goes to form copper plus nickel 2 chloride. And aside oxidation numbers, oxygen or nickel is 0, copper plus 2 because chlorine's -1 and there are 2 of them, so therefore we deduce this. And same story, we know that there are 2 chlorides each at -1, therefore that nickel must be +2. So we see nickel went from 0 to +2, became more positive, that must have been oxidized. And chlorine went from -1 to -1, so it didn't change, but copper went from +2 to 0, so it was reduced. Okay, so what question did they ask? They said, what is the oxidizing agent? Remember, the oxidizing agent is not oxidized because it helps something else be oxidized. Therefore, this would be the oxidizing agent. Okay. The copper specifically was the oxidizing agent, but the copper came as copper chloride. They don't give me the option for just copper. So copper chloride, because it gets reduced, therefore it causes oxidation. That's why it's the oxidizing agent. All right, so that's oxidation and reduction. The rest of this looks at solubility and precipitation reactions. And you've got some solubility rules here, and if you like them, you could follow them. That's just fine. They're a little bit more complicated than the ones that I give you in the lecture notes. I think in the lecture notes, we don't talk a lot about phosphates and hydroxides and sulfides. We just kind of cover the first 4. But the key is nitrate, acetate, ammonium, and alkali metal cations, that's sodium, lithium, potassium, etc. Those are always soluble. And you go in order. So if you hit these and it says soluble, then you know it's soluble. Chlorine, bromine, iodine, always soluble unless you're silver, mercury, or lead. And sulfate soluble unless you're strontium, barium, mercury, or lead. Okay, so then we look here and we say zinc and nitrate. Oh, all nitrates soluble, so we're going to toss that in the soluble bucket. Magnesium and chlorine. Ooh, chlorine's always soluble unless they're with silver, mercury, or lead. This is magnesium, not silver, mercury, or lead, so we're going to say soluble. Iron chloride, again, all chlorides are soluble unless silver, mercury, lead. That's not silver, mercury, or lead, so we're going to predict soluble. Iodine here, iodide compound soluble except for silver, mercury, and lead. Ooh, this is, in fact, that looks like a funny thing, but let me show you. Hg2, 2+. This is the polyatomic ion known as mercury 1. Looks like each mercury atom has a charge of +1, but they actually come in a group of 2. So it looks like you should be able to reduce that to HGI, but you can't. Anyways, this is iodine with mercury. That's one of the exceptions to iodine being soluble. So we would predict that would not be soluble. Okay. All right. Hydroxides in general are not on the list. The list that I give you is just these first 4 bullet points. And if neither the zinc nor the hydroxide is on the list, then you can predict it's probably not going to be soluble because these are the list of all of the things that are soluble. So I would say not soluble because hydroxide and zinc are not on the list. Now, if you're following the slightly expanded list in your textbook, or here it says hydroxides are insoluble unless, well, we already knew that ammonium and alkali metals are soluble. So that doesn't tell us anything new. And this is not calcium, strontium, or barium, so yes, that would definitely be insoluble. Okay. Oops. Potassium nitrate. Rule number 1. Nitrates are soluble, so we're going to stick this in a soluble pile. Strontium sulfate. Sulfates are soluble unless you're with strontium. Okay, so insoluble. KBr, alkali metal cations, potassium, always soluble. notice how if I could just identify one of the ions, that I could just dump it in one pile or the other, because I go in order, right? This is the first thing I hit, the second thing I hit. If one ion is soluble, barring any exceptions, then the whole thing is soluble. All right, NaCl, again, this is alkali metal cation, because it's in the first group. Sodium is always soluble, so that will be soluble. No additional ones there. There we go. Now you have to memorize the solubility rules. Again, just these first four, basically the ones in my lecture notes. You need to know those so we can predict reactions like these, right? So, looking at these reactions, are they going to make a precipitate? Or in other words, are they going to make something which is not soluble? So you're going to have to say, is this soluble? Is this soluble? If there is something which is not soluble, then it will be a precipitation reaction. It will have a precipitate. If they're both soluble, then it would not be a precipitation reaction. So in this case, potassium nitrate, rule number 1 says nitrates are always soluble. So that will be soluble. Rule number 2 or 3, if you're using the ones on this particular tool, says that bromine, chlorine, iodine are always soluble unless they're with mercury or lead or, what was the other one? Silver. That's right, silver, mercury, or lead. So because this is with lead, Pb is lead, then PbI2 would be a precipitate, and this would be a then precipitation reaction. Then. Okay, here we go. We've got mercury acetate plus sodium chloride. I've got mercury chloride and sodium acetate. I know that the sodium acetate will be soluble because the first rule says that acetates are soluble, as well as group 1 ions, which is sodium. But the next rule says that halides, like chlorine, are soluble unless they're with silver, mercury, or lead. And in this case, it's with mercury. So here we go. That's our exception. Chloride with mercury, not soluble. That would make a precipitate. In the next case, we have HBr plus KOH. I get KBr. Potassium is always soluble because it's in group 1. And H2O is a liquid. That's just water. So no, I'm not forming a solid. Nothing which is insoluble, so that would not be a precipitation reaction. In this case, hydrogen peroxide and ACLO. Salt is soluble because group 1, sodium, always soluble. H2O is water, so that's not a precipitate. That's not forming a solid. And oxygen is actually a gas. This is a gas-forming reaction, but no solid is going to be formed, so it's not a precipitate. All right, next, HCl plus KOH. KCl, soluble, because K is a alkali metal. Alkali metals are always soluble. And H2O is a liquid, again, so not a precipitation reaction. Next, barium nitrate plus potassium sulfate. Barium sulfate, our rule says sulfates are always soluble unless strontium, barium, oh, that's what we've got. We've got barium and sulfate, so that will not be soluble. That will form a precipitate. And then the potassium nitrate will still be soluble. Potassium and nitrate are both always soluble. And here we've got carbon plus oxygen making carbon dioxide. Carbon dioxide is a gas, so not a precipitation reaction. Okay. Next, identify the precipitate of the reaction that occurs when a silver nitrate solution is mixed with a sodium chloride solution. So I see words. That's not helpful to me, so I'm going to write it out. Silver nitrate, silver's +1, nitrate is NO3 with a -1. The charges are going to balance, so that is silver nitrate. And sodium chloride, sodium is +1 and the chlorine is -1, so that also balances. Okay, now I need to predict the products, which is easier than it sounds, because at first you might say, I don't know what's going to happen, but remember, cations are always listed before anions. Positively charged ions are not going to react with other positively charged ions. So my only option is to mix this silver with the chlorine, because this is a cation and this is the anion. And then the nitrate with the sodium, because this is the anion and this is the cation. So you'll always have the outsides combining and then the insides combining. So our product here then is going to be the Ag, which is +1, and the Cl, which is -1, and the Na, which is +1, and the NO3, which is -1. And then which of these is a precipitate, if any, or both? We can look at our solubility rules, and we see that chlorine is always soluble unless it's with silver, mercury, or lead, and that is silver. So this is going to be a solid. And then sodium and nitrate are both always soluble, so that's not going to be a precipitate. So our silver chloride is the precipitate we're going to get there. Okay. There's the whole thing written out, including your phases. All right, soluble or not soluble. Here we go. Sodium, always soluble, because it's a group 1 or alkali metal. Barium sulfate, let's see, rule 3 says sulfates are always soluble unless they are with barium, mercury, or lead. Oh, that's barium, so that would not be soluble. Lead sulfate. Sulfates are always soluble unless they're with barium, mercury, or lead. That's lead, so that would not be soluble. Ammonium phosphate. The rule 1 says ammonium is always soluble. So ammonium with anything else, including in this case phosphate, we're going to say soluble. And magnesium sulfate, our rule says sulfates are always soluble unless barium, mercury, or lead. Since that is not barium or mercury or lead, then we're going to assume that that will be a soluble compound, right? All right, the combination of ions most likely to produce a precipitate would be what? Let's see, ammonium is always soluble, so we can skip that. Acetate is always soluble, so we can skip that. Nitrate is always soluble, so we can skip that. Neither of those are listed on our table of solubility rules, so that looks like it's a good candidate. But let's check this last one. Nope, lithium is a group 1 or alkali metal, so it's going to be always soluble, so it's not that. So it's the iron and the hydroxide, because neither of those are listed. So there's 2 ways to determine if something's going to precipitate. Either it's neither of the ions are listed, or you're looking at an exception to the ones which I told you were always going to be soluble. All right, precipitation reaction, same story. Here we're going outsides. We're going to get a nickel sulfide, and insides gives us an ammonium chloride. And if you eyeball this, you know that ammoniums are always soluble, but nickel and sulfur, neither of those are listed on our list of things which are soluble, so we can presume that the nickel sulfide would form a precipitate. So again, same story, outsides and insides. Silver goes with bromine. We know that halogens, chlorine, bromine, iodine, are always soluble unless they're with silver or lead or mercury, and in this case, yes, it's going to be with silver. So we can predict that the silver bromide will be a precipitate. And then, of course, doesn't matter what this is because we already said it would occur, but the nitrates are always soluble, so the calcium nitrate will not be our precipitate. It's going to be the silver bromide. All right, and which of these will not form a precipitate? Well, okay. Potassium with acetate. The acetates are always soluble, as are potassium, since that's group 1. Barium with chlorine. The exceptions for chlorine are silver, lead, and mercury, so we wouldn't expect a precipitate with barium. So I'm looking at this one and thinking I'm not going to see a precipitate. Ag with Cl, yep, silver is one of my exceptions to chlorine being soluble, so that would form a precipitate. Outsides, barium with sulfate, yes, barium is one of the exceptions to sulfate being soluble, so I would expect this to result in a precipitate. And finally, outside sodium with nitrate, that would be soluble. Insides lead with carbonate. Neither of those are on our list of things which are soluble, so I would expect that to be a precipitate. You see how important it is to be able to quickly and easily identify polyatomic ions and be able to pick apart these ionic compounds. So one of the reasons I have you memorize the polyatomic ions is so that you can see them quickly and do reactions with them in a timely manner. Should kind of pop out at you. Okay, spectator ions. What are these? All right, I've cleaned up my little drawing area here. And what we're looking at for spectator ions is ions which aren't involved in kind of the action, but rather ions which just watch the show. They're not doing anything, they're just spectating. So if we pick this apart, we've got 2 silver nitrates, both dissolved in the water because we're soluble. And we have K2SO4, soluble. And we go to form 2KNO3, soluble, plus Ag2SO4, solid, according to the way this is written. Okay, so they've given us a reaction and they've told us that this is a precipitate. So your job first is to remember that ionic compounds, if they are soluble, they are actually dissociated from one another in solution. So I don't really have a solution with little silver nitrate molecules running around. I've got a solution with silver ions and nitrate ions running around. And I'm mixing that with another solution which doesn't actually have potassium sulfate, but it has individually potassium ions and sulfate ions. Now for the moment, don't worry about balancing here. We're just trying to see what species are existing in the solution. So this is the first solution. I'm mixing with the second solution, but both solutions just have a bunch of ions running around. Okay. In the product, because this is an ionic compound and because it's still dissolved, we know that what we really have are potassium ions running around in solution and nitrate ions running around in solution. And then because this is a solid, now it is not dissolved in solution, therefore it is not dissociated. So this is exactly what it is. It's a solid. So a spectator ion is something which did not itself participate in the reaction. It just kind of watched. It didn't do anything. So anything which has not changed from reactant to product would be a spectator. So nitrate is nitrate on both sides. Aqueous nitrate, aqueous nitrate. And potassium is aqueous potassium on both sides. So what did change is the silver reacted with the sulfate to make silver sulfate. That's what actually happened. And the rest of this just came along for the ride, but it didn't actually participate. So those are the spectator ions. Spectators. Potassium and the nitrate. Spectators. All right, examples of an acid-base reaction. What we're looking for acid-base reaction is some sort of acid. This is what we're going to look for an acid. It contributes an H plus or hydrogen ion. Some sort of base contributes OH minus or hydroxide ion. And those will combine to make H2O, water, as a liquid. This is aqueous, aqueous, liquid. Okay, so the H is going to come from something, the OH is going to come from something, and I have to make water. So for instance, if I'm not making water, I can eliminate it, right? So this is not an acid base. This is not an acid base. They're trying to trick me into thinking that's water, but that's not water. That's HGO, not H2O, so that's very silly. Can't be that. Both of these top two reactions do form water. So now we have to say, okay, which of these top two reactions does it appear that I've got some sort of aqueous hydrogen reacting with an aqueous hydroxide? That wouldn't be the case here because I only have one thing here. This is a decomposition reaction. But here you can see the H2SO4 as an ionic compound splits up and would donate, that would end up with H plus ions in solution. The calcium hydroxide as a soluble ionic compound in solution would split up and contribute hydroxide ions to solution. So we have the H plus plus the OH minus. That's what gives us the H2O liquid. They're kind of like precipitation reactions where you're very specifically making, instead of a solid precipitate, you're making H2O as a liquid. That's your acid base. Okay, so write and balance these acid base neutralization reactions. Here we go. So they want the whole chemical equation, not just the product. And they want you to identify phases like aqueous in your answer. So I have CSOH, and that's aqueous. And I have H2SO4. That's aqueous. Oops. If you guys are wondering how I did that, if you've ever noticed this little keyboard thing up here, that'll tell you shortcuts. And for instance, you'll see if you click on that, it'll open up a new window and you can say, oh, this is really quick. If I want a subscript, then I just do an underbar on the keyboard and that puts me in subscript notation, and so on and so forth. For the rest of these, that's what I was doing. All right, so that goes to form. That was just a line with a little side arrow that automatically turned into an arrow. That goes to form what? We're going to play the same game as we did for the precipitation reactions. Outside ions combine, inside ions combine. So we have cesium combining with sulfate. Oops. Now, I'm not done with that because I have to remember cesium's in group 1. It has a charge of +1 by definition. Sulfate is a polyatomic ion with a charge of -2 by definition. So I have to have 2 cesiums to cancel out the charge that will be contributed from the sulfate in order to have the right equation for the cesium sulfate. Now cesium is a group 1 ion. It is an alkali metal, and all alkali metals are soluble, so I can predict that that product will be soluble. And then inside ions I have hydroxide combining with hydrogen. That's H plus because it's in group 1. Hydroxide is defined to have a charge of -1, so +1 -1. I get 1 H with 1 OH, so I could write that as HOH, but really that is H2O, right? That is classic example of acid and a base exactly like I was showing you here, which is good because they told me that these were acid-base neutralization reactions. So here I have cesium hydroxide plus sulfuric acid going to form cesium sulfate and water. These are soluble, 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 and this is, of course, a liquid. Doesn't need to be soluble because it is the liquid that you would be considering. Now they did say balance, so write and balance. So we do have to note 1 cesium here, there's 2 there, so we better put a 2 there. And we have 2 hydroxides and 2 hydrogens. That's going to add up to 2 waters. And then we have 1 sulfate and 1 sulfate. So that should work. All right. A lot of different moving parts to this one. Challenge to get, but that's how you go. That's how you do it. Okay. Next, same story. I wonder if it'll let me copy and paste that. Ooh, that was nice. I just have to come along here and say, make that a subscript. But that sure made my life easier, didn't it? I just did a Control C and then a Control V to paste, and then that's the first half of my equation. All right, so outside ions, Na plus, Br minus, that makes NaBr. Sodium's in group 1, always soluble. Done. All right, inside ions, H, HCO3. The H has a charge of +1. This is the bicarbonate ion. It has a charge of -1. So one of each, that's going to give me H2CO3. All right. And at this point, you know that those are all soluble. You might be tempted to be done. Sodiums are balanced, bromides are balanced. Everything's balanced. What you don't know, because I didn't teach it to you and I'm not going to test you on this, but what they want you to add in here is that HCO3 or H2CO3 as a compound actually spontaneously decomposes to form water and carbon dioxide. It's a gas forming reaction. It forms a gas and a liquid. So this is a little bit like an acid base, because this is your acid and then this is a kind of more complicated base, and then you do eventually kind of get water out of that. So that was a trick. Not meant to be a trick question, but I think I wanted you to do part A and got stuck with part B as we were at it, and I figured it's okay to expose you to the idea that there are gas forming reactions and that this kind of decomposition occurs. In fact, we saw this decomposition reaction just a couple problems ago when we were asking which of these are true acid-base reactions. Anyway, so this is the reaction I think that they want. Yep, there you go. All right. Next, milk of magnesia is a suspension of solid magnesium hydroxide and water that is used to neutralize excess stomach acid, which is aqueous HCl, and they want the balanced chemical equation for that neutralization reaction. All right, so solid magnesium hydroxide. Magnesium's in group 2, it has a charge of +2. Hydroxide is a polyatomic ion which has a charge of -1. So I'm going to need 2 hydroxides for every 1 magnesium. And they told me it was a solid, which I should have known because, of course, according to my solubility rules, neither magnesium or hydroxide are represented, so we can presume that put together would not be soluble. Now that's neutralizing or reacting with excess stomach acid, that is HCl. And they told us that it was aqueous, which means it does dissolve in water. All right. And then we're going to put the outside ions together, magnesium with chlorine. Magnesium's +2, chlorine's -1. So I'm going to need 2 of those. And the inside ions, the H with the OH, it's just the same that we had up here. That gives me water, right? And they want us to balance it, so 1 magnesium, okay. 1 chlorine, 2 chlorines, so I'm going to need a 2 here for 2 chlorines. And then 2 H's with 2 OH's should give me 2 H2O's. And we're also going to need to say chlorine soluble unless it's with silver, mercury, or lead. This is none of those, so it's still soluble. And water that is a liquid. So that's the whole thing that they want in here. Right, let's move that so I can see. Magnesium, ooh, just Mg. OH2 is a solid, plus 2 HCl's, aqueous, goes to form magnesium Cl, Cl2, aqueous, plus 2 H2O's. Oh. All right. Magnesium hydroxide, solid, plus 2 HCl's, aqueous, makes magnesium chloride, aqueous, and 2H2O liquid. Right. Okay, net ionic equation for the reaction shown. Net ionic equation is what you get when you remove the spectators and you say, listen, you're not really part of the equation, so I'm going to remove you. What's left is the net. Ag plus SO4 2- makes Ag2SO4. So let's figure out this reaction, pull out the spectators, then we can determine the net ionic equation for it. So what we've got, barium hydroxide plus sulfuric acid goes to form what? Okay, outsides, barium with the sulfate. Barium is +2, sulfate is -2, so I just need one of each. And sulfates are always soluble unless they are with barium, mercury, or lead. In this case, there's barium, so that's going to be a solid. That's going to be a precipitate. And insides, H goes with the OH. Oh, that's water, which is in fact a liquid. So for here, when we took the complete molecular equation, everything is represented as a molecule. Everything which was aqueous, we could split up into ions, and then you could cancel out ions, right? So if we pull this out, we've got barium 2+, aqueous, hydroxide, aqueous. We've got H+, those are aqueous, and sulfate, which are aqueouses. These are not aqueous, so I can't split them up because they're not dissolved in solution. Okay, can't split this up, and this is a liquid. So there's nothing to cancel because there aren't individual ions on this side. This is both a precipitation reaction because I made a solid and an acid-base reaction because I made water with the H and the OH. So the whole thing is going to be there. Okay, goes to form barium sulfate, solid, plus water, liquid. Okay. All right, so that's it, the whole thing. Now I was showing everything as individual ions, and they've included the coefficients to make sure that's still balanced. This ion and this ion are in one solution, and you combine them with another solution which contains these two ions, and we get both a solid precipitate and a liquid. That is it. Okay, last problem. Classify these as precipitation, acid-base, or oxidation-reduction. Ooh, excellent. A little bit of a shortcut. If I have double displacement, then it's usually precipitation or acid-base. And other reactions, for instance, synthesis or decomposition, usually fall into the redox category. Okay, so this is double displacement. Outsides, Ag and Cl go together, insides go together. Aqueous, aqueous, solid, aqueous. The presence of a solid is a dead giveaway. That's a precipitation. In this case, solid, liquid, solid. That doesn't really scream of acid, base, or precipitation. Ooh, this is a synthesis or combination reaction. So could be redox. Let's look carefully. We have elemental aluminum, oxidation number of 0, elemental bromine, oxidation number of 0. Now I have an ionic compound, aluminum bromide, their charges +3 and -1. Absolutely, oxidation numbers changed, so that's a redox. And the last one we have, this is double displacement. The calcium went with the nitrate. H went with the OH. Aqueous, aqueous, liquid, aqueous. Oh, we are making water. Here's the dead giveaway. I'm making water as a liquid. And yes, indeedy, that came from H and OH. That is an acid base. Neutralization. That's how you do it. I hope this was helpful, and I hope you all have a lovely day.